Welcome to SOH, the best office hours ever, because you are part of it. 2023, number 3. Let's go over and see what's about. And if we need to go more in detail, then I will talk about it later on. But maybe you have enough with just introduction for most of it. And otherwise, you will see all the details in order to get above a 5 here. A bottle of milk. Okay, good. I hope you like it. Is taken out of a refrigerator and placed in a pan of hot water to be warm. Okay, that might be a very old way to warm it up. We have microwaves today. The increasing function m models the temperature of the milk at time t, where m of t is measured in degrees Celsius. Okay, so keep track of the units, because this is an easy way for them to catch some little things and get your points down. So if there are units, use them. Sometimes there are none, like in integral problems with areas, but there might be. If there are units, again, just highlight them. And minutes. What else? Oh, we have a differential equation. I like that. And you will also love differential equations soon, because you'll see that basically we have to do more or less the same steps, but they describe how things change in time in a detailed way. So that's kind of cool. Now, at time t equal to 0, the temperature is 5 degrees Celsius. That's an initial condition. That's used to know precisely when we integrate the differential equation where we are. It's like if you look at this plot here, that we will talk about it later, you know, there are many possible curves here. You could take like this one, or this one, or this one, and so on, or even this one, this one. The initial condition will tell you which of them you are, okay? So let's read the questions. A slope field for the differential equation is shown, so here, sketch the solution curve through the point 0,5. This is a very welcome question, because you need to join the dotted line. That's it. Of course, from 0,5, so from here. Then what is here? We will do that, but that's basically what you have to do. You have to be careful not to cross it or not to do something weird. Okay, that will be wrong. We will do it in a second, but just follow it smoothly, and that's it. Don't worry too much. They just want to see you that you know how to join some dotted lines. So fine, great, thank you. Now, use the line tangent to the graph. Line tangent to the graph, that's another keyword. Line tangent to the graph. Why is that a keyword? Because this is telling us to use this approximation. So that's for question B, okay? That the value of a function at some point x equals the value of at x0 plus the derivative at x0 multiplied by x minus x0, plus other terms that we neglected. So that's the approximation of the line tangent. So we need to know the derivative, but the derivative is here, right? We need to know what else? Yeah, the value of the function at that point. And then we also need to know the value of x. So we also need to know what's x here, but they want to be 2. So we will deal with it, but basically you have all the information that you need to solve this. What's interesting about this problem is the next question, because it says write an expression for the second derivative to find out whether there is an underestimate or overestimate. That's kind of the cool thing here. Why? Because when we use this formula here, it's an approximation, we would like to know, well, how good it is, right? Is it an overestimate, an underestimate, and how much? Without further information, we cannot say anything. But with the second derivative, we can say something. Look at this plot. You have a function that is not a line. Let's say something like this. And we have an initial point here, okay, x naught. And we would like to know, you know, this is a true value, right, at x, okay? But we would like to know how much is this if we start here with a line. If we start with a line, we are not going to get curved, so it's going to be just straight. And look at that, we end up higher. So if the curve has this kind of curvature, like a maximum, right, then it's going to be an overestimate. This is going to be an overestimate because it's above. If it would be the other way, it's an underestimate. So that's being told by the curvature. And the curvature is related with the second derivative. So knowing the value of the second derivative will tell us what's happening. And then finally, for D, let's go to D here. D, the final thing, separation of variables. To find this expression, to integrate it. Okay, separation of variables, the word separation says to separate. So you will separate like brothers with brothers, sisters with sisters, then you will integrate and it will be a happy family, okay? Now, that we need to know which are the brothers and sisters. Brothers are going to be the m's because it's one of the variables, so these are the brothers, and the sisters are going to be the other variable, which is t. We will separate them, and we will deal with them independently and join them together in a final solution that will have these initial conditions. It will tell us exactly, as we were talking before, which one of these curves are we considering, okay? Which one of these. So let's begin one by detail. If you had enough until now, great for you. Get for the 5. Otherwise, if you continue, we're going to get to a 6. So border of meal again. Okay, I had enough meal for now. A slow field for the differential equation is this one. Sketch the solution through the point 0,5. Yes, yes. So remember, just join these dotted lines softly. Sometimes you don't find one, but you know, like this. And then you see it's horizontal. Don't cross it because it's just flat. You cannot cross it. A wrong solution could be something like that, right? Like this, and then I go happily, and then I go back. That would be wrong. Or I don't know, something like this, right? Don't do that. Probably you wouldn't do it, but if you see a friend of you doing that, tell him or her not to do it, okay? So that's it, nothing else. You don't need to worry. I mean, if you have enough time, then just draw it like asymptotically here as much as you want, you know, but make sure that it doesn't cross it. Remember, if you count everything 5, 10, 15, 20, 25, 30, 40, okay, so that's exactly what they were saying that here, remember, that it never crosses 40. So yeah, that's true. So that's our solution, okay? This kind of thing here, very thick, but that's it. Okay, let's move on because we have more things to do with this milk. Use the line tangent to the graph to approximate the temperature at t equal to 2 minutes. Okay, so remember the important thing here is to use this expression, that a function can be approximated if we use the line tangent as the function at that value plus the derivative multiplied by this. We know that there might be an over or an underestimate, so this is just kind of to begin with. Now we have to translate this into our problem. So what is f of x? It's going to be m of t. What is f? Well, it's going to be at the initial time. Okay, what is this? The derivative at the initial time. And this is time minus time. Now, let's identify each of these things. M of t, we don't have it. That's what we want to find out. But we have that t is going to be 2 minutes. Okay, so we want to find m of 2, basically. So it's going to be approximately m of 0 because they tell us to consider t equal to 0, right? Plus the derivative at 0 multiplied by 2 minus 0. So basically, we have to substitute what we know. This approximate, so let's make sure approximate. M of 0, well, we have it that m of 0 is the initial is 5 degrees. Here it is. Oops, sorry about that. Let me move it back. So 5 degrees. So we have that is 5. Now, what is the derivative at t equal to 0? Well, you have that dm over dt equals 1/4 of 40 minus m. So the derivative at the beginning at t equal to 0 is going to be 1/4 of 40 minus the value of m at the beginning, which was 5, remember? So it is 35 divided by 4. 35 divided by 4. Just one detail, optional. The optional thing is that there are units here, right? So this has units of degrees Celsius per minute, okay? If you want, because that's the derivative. If you plug this thing here, then you have that this is plus 35 divided by 4 multiplied by 2. And this is equal to 5 plus 35 divided by 2, or 45 divided by 2, which is 22.5, and very, 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 very important, degrees Celsius. Very, very, very important, okay? So that's the value. The answer is therefore that the approximate temperature is 22.5. Now, is that an overestimate? So is the true temperature below 22.5 or an underestimate? And therefore the true temperature is above 22.5. I know that you want to know because you want your milk to be at the right temperature to be drunk, right? So let's see what these people thought for us. Okay, write an expression of the second derivative. So next time that you drink a bottle of milk that you're warming up, remember, compute the second time derivative before you drink it. Let's do that. So, yep, I'm not joking. So, second time derivative with respect to the milk is this thing here. Okay, of the first derivative. Now, let's be serious about it. So, what we have is this thing, yes. And you can see that you can apply, it's the derivative of a product, and the first term is a constant, so it's going to be like that. And then you have to take this time derivative of this, right? Now, the time derivative of 4 is 0, and minus m is the derivative of m. So what you get is basically, let's put it here, 1/4 minus 1/4 of the derivative of m with respect to t. And it's kind of recursive. It goes back because you have that this thing here they were telling us what it is this thing here, right? So we just need to substitute it back. So, okay, minus 1/4 and 1/4 of 40 minus m, okay? And this minus, we can change the order of the operations, and then 16. Okay, cool. So that's the second derivative. At any point, where do we want to know this curvature? Remember that we have this curvature here. We started from this point, from t equal to 0. You can evaluate it here. How much is the curvature here? We want to get to t equal to 2. So, well, if this function would change a lot, it could change the curvature along the way. So the right thing to do would be to investigate what is the curvature here, right? Because that's where you want to see whether there is an overestimate or not. But in these problems, you don't need to go to that level of detail. You can always use this value here. How would you deal, however, if you would like to know this? Well, we just answer how was M2 approximately in question B, right? So you could use that instead of the value at 0 to know how much is this curvature. But for the AP test, you can always use the initial point. So let's compute how much is the second derivative at t equal to 0. And it's going to be the value of m at equal to 0. Be careful, this is not 0. This is not 0. This is whatever it is. So it is 5 minus 40 divided by 16. Okay, so I have to substitute things properly. And you get this expression. The value itself is not relevant. What we want to know is the sign of it. And if it's negative, just remember that if it's negative, it's like the maximum, or something like this. If it would be positive, it would be like the minimum. And then just plot your line. Clearly, it's an overestimate. So you can jump directly here and say, look, since, you can say this, since the second derivative of m at point t equal to 0 is negative, then it's an overestimate. That's it. End of the story. Okay, you don't need to, but just do your drawing, and with the drawing you will find easily if it's an or if it's an underestimate. Okay, so you will see that we are in this case the second derivative of m was negative. If you would have substituted the point equal to 2, you would have gotten the same result that is negative. It doesn't change across the point, but you don't really need to do that for AP calculus. You know, maybe in the future you want to be more precise and do that just to make sure that the curve does not change in between t equal to 0 and t equal to 2. Okay, just keep that in mind. It might happen sometimes. Okay, in college. So let's see. What do we have? Oh, the last one. Separation of variables. Yes, happy family. So let's see that. Okay, we have this equation here, and we want to separate the variables. Okay, cool. So let's do that. What are the variables? Variables are going to be, one is m and t. Left or right? Well, up to you. Freedom of choice. The act of freedom of choosing right or left. That's another act passed by the Congress. So you can choose m to the right or to the left. I would choose to the left because we have, dm on the left. And then, however, you get this denominator, right? So, well, but we have the dm here at the top. That's going to make things easier to integrate. And then multiply here by 4. Don't forget that 4 and dt. I like the 4 here because it's in the numerator. But now let's be careful because we have to integrate this. So let's not forget that we have a number 4 here. We have this, and then we have this. Now, the right-hand side, it's great. It's just t plus some constant, right? Arbitrary until when? We use the initial condition. We use the initial condition, always, okay? Always, okay? Always. So this question has an advantage that, as you will see, is always the same steps, but it's long. That's the drawback of this question. So let's do that. Let's integrate on the left-hand side, and on the right-hand side we already did. So how do we integrate this? Now, be careful if I do this because I may forget, that's very important, this number 4. So let's not forget it later, okay? And, well, so this is just a logarithm, but how do I know? If you know it, I'm going to write the solution for those who know. Okay, plus another constant. Now, how do you know that? Because this integral that you may have studied, right? It has an absolute value here, by the way, it's important, plus a constant. So the absolute value is important. Though, just keep it. It's the best way to do it. Whether we can get rid of it or not, we will see it later. Sometimes yes, sometimes no. So just keep it always. But we don't have exactly the same expression, right? So how do we join both things? Well, one way of doing that is the following. Let's add a new page better. Yeah, blank page. It is a change of variable. It's what is called a change of variable. So you simply get your integral into an expression that you have memorized, or you have it in a tables of integrals. In this case, we would like to change, right, the denominator here. This denominator, we would like to call this kind of x, right? So instead of x, usually one uses the letter u, okay, for the new variable, because it could be an x here. So u is going to be this. Okay. The next thing to do is to compute the derivative of this change of variable. So if you compute the derivative here, derivative, what you get is u prime equals minus, and then you derive with respect to your variable is m minus 1. That's it. So with respect to m, okay, not x or t or whatever, just your variable, okay, m, your original variable, minus 1. Then your integral, let's say a general integral that is a function of m dm in general, is going to be, with the change of variable, it's going to be this thing, and then divided by u prime. That's one way of doing it. There are other ways of writing it, okay? Maybe you have learned a different way to do it. But in any case, you get to the same conclusion. So in this case, it would be, you change the dm by du, you change your function 1 divided by this, so 1 divided by u, and then be careful, you have 1 divided by the u prime, okay? Don't forget this term, which is very important. In our case, this is minus 1, so it's this thing. So you get this, which is the one that we studied, okay? Now let's join all together, and that's where it becomes very important not to forget this number 4. So that's very tricky. 4 times minus logarithm of this plus a constant equals time plus another constant. So I don't know, let's call this constant 1 and this constant 2. Now, if you have an arbitrary constant and you sum up or subtract another arbitrary constant, it's going to be another arbitrary constant, right? So in this case, don't worry too much about the constants. It's just minus 4 logarithm of u equals t plus some constant. And some people don't even write C3, C1, C2. It's just the same C. Understanding that it's a new constant. And since it's arbitrary, you don't need to keep track of all the labels. Okay, now this is still not yet the solution, because we have u. I mean, not u, but the letter u. And we are going to change that by the original expression. Remember that u was not u. I'm not calling u 40 minus m, but that was the letter, 40 minus m. Now we have to get m. That's the key thing that we have to get. So, well, let's try to isolate that. So it's going to be logarithm of absolute value of u, still the absolute value. Okay, I know I am repeating myself a lot, but I've seen this many times. And then it will be a new constant, because it's divided by minus 4. Okay. Now, finally, this expression resembles this thing, and you know that x equals e to the power of y in this case. So that's what we are going to do. So as I said, these problems are always the same steps, but can be a little bit long. So let's go there. We had logarithm of u. Let me copy it again. We just missed the super arbitrary constant, but this means that our absolute value of u is this thing here. Okay. Now, here comes another thing. E to the power of a plus b is the product of these two things. Okay, remember that a long time ago, but we need it here. So this means that our absolute value of u is going to be this multiplied by this. And again, an arbitrary constant, the exponential of an arbitrary constant, what do we think it is? Another beautiful, gorgeous arbitrary constant. Oh, C5. Oh, we have 5 already. Okay, we are collecting beautiful arbitrary constants here. Now, the point is that now we could use the initial condition, but before that we can finally write what was u. So u here, not there on the screen, is 40 minus m of t equals C5, this thing. So finally, sorry for the delay, thank you for bearing with me, you have this. Okay, cool. That's why sometimes if you read at the beginning of the problem separation of variables, try to get the first questions a little bit faster, not too fast to have a typo or an error, but little bit faster and get into this one. And you can see that this one is mostly independent of all the previous ones. You can also start with this one, which is longer, and then you manage how much time you have left for the other ones. Because it's always good to double check things, right? So you could directly start with this one, honestly. Okay, so where's our wonderful thing? Oh yeah, we have to remember our initial condition. So how much was that? I know you remember, but my brain has forgotten about it. Oh, that's a joke. It's 5 Celsius degrees. Let's see. Yes, I got it. I'm still awake. So I hope you are too. So this is 5 Celsius. And then let's substitute this thing. So 5 equals 40 minus, and here we are about to know our gorgeous arbitrary constant, which is C5. Well, remember this is number 1. Excellent. And what we have here is therefore that C5 is 35. Amazing. And if you want, it even has units because, you know, these are degrees, Celsius degrees, Celsius degrees. This must also be the same. So you don't need that. That's optional, you know, optional, but it's not bad. So what you have finally is that, where are we? Yes, here, 40 minus 35, and then e to the t minus 4. And that's amazing. And that's, I mean, this is like, I mean, a plus, 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 at least. So that's it. However, I would like to tell you, if you would like to double check that this answer is correct, how do we do that? Well, there is 2 things that we can do. So this is optional. If you're done, you're tired, just go to the next one or enjoy the rest of your day. Hopefully the latter. But if you have some more time and you want to know how to double check this, there are 2 ways that you can double check this, which is important if you're in a test that you are, after 1 year, you want to get a 5 and get done with it, right? So if we go back to the diagram with the arrows some time ago, like 3 years ago, here, let's go even here. So you can see that our graph was something like this, right? And it was approximating 40. There was kind of an asymptote here. Yes. So if we go now here to our solution, let's see where does it go. Okay, finally here. No, not here. Yes, here. So what happens if t goes to infinity? Like long time. Then you know that this guy goes to 0. The thing that we don't want, right? 0. But it goes there. So what is the conclusion? That this is going to go to 40 minus 35 times 0, which is 40. That's exactly what that graph was saying, and also the wording. It was approximate. It was always less than 40 degrees. So this bottle of milk, after a long time, is going to get into 40 Celsius. Okay. Of course, this is approximate because if you wait a couple of days, it's going to go to the room temperature, and that's it. But anyway, for this problem, that's one way of verifying the solution. Another way of verifying the solution, if you have plenty of time, and I'm sure that you will have plenty of time because you're going to get at this super good, is to say, well, okay, you know, I have so much time that I'm going to compute this derivative. And I'm going to match this with the wording of the problem. So how do you do that? Well, let's take the derivative, 0 minus 35. Then here you're going to have minus 1/4, and this thing, okay? We just rearrange this a little bit, so 35 divided by 4, and then we have this. And then what do we do with this? Well, you can see how this combination here, it's also here, right? So that's a trick, and it always will happen the same thing, always. So you will identify that this, let's say, an expression that doesn't tell us anything, it can be related with the initial function. So this is indeed, if you look there, is basically 40 minus mt, right? So if we write now that here, what we get is exactly what they said at the beginning of the problem, the differential equation of that bottle of milk. So let's see if that's true. We have this, and then we go back to the problem. Yes, here it is. So the problem is correct, okay? Well, thank you so much. I wish that you've learned something, and you can apply that in your next problems, and see you in the next exercise.